So this is going to be the last section of module 5, right, which is ADC and DAC. Very interesting topic, right, where conversions happen between the analog side and the digital side, which means whenever I say ADC, it means there's a conversion from analog form to digital form, and here is a conversion from digital form to analog form. So to understand this, we'll have to look into a few waveforms. We'll have to look into some theory behind it, right? We'll have to look into some circuit analysis and how this conversion is actually done. Okay, fine. So before we get started, let me just give you a small introduction as to what is this conversion and where do we use it, right? Now, let's say we have a plant, okay, and it has a sensor. A plant can be probably any manufacturing plant, for example. Okay, so it will have a sensor or a transducer. So sensor will actually send information in the form of analog signal. Like my voice is right now analog, but then when it's getting transmitted on the digital platform, right, it's broken up into discrete values, right? It's broken up into these kind of discrete values, and once it's broken up, it becomes a bits and pieces of a digital platform, right? So here, when we're talking of digital information, right, it's all about zeros and ones, isn't it? So when we're talking of analog, it is continuous with respect to time. See, I have put this waveform here, okay, where in red, okay, you can see it is continuous with respect to time. So at any instant of time, I can actually check its value, and I can go to that particular point and check, how much is the value. But then in, discrete or in digital form, that's not going to happen, because we're going to have values in, different instances of time, right? Okay. So analog signal is sent to anti-aliasing filter, and then I will look at this band limited analog signal. Then I'll be sending it to sample and hold circuit. Sample and hold, I think you would have done in your experiments, right? Where it is sampled for a time and then it is held for a certain amount of time. So this line that you see here, right, from the left to the right, is nothing but sampling, and from down to the top, okay, is called holding of value. So sampling is here and holding is here. So sample and hold, that's about sample and hold circuits. Then this is going to be in discrete form, right? And then here I'm going to use an ADC, right, which is nothing but analog to digital converter. So when it is digital, all this will get converted. This continuous wave will actually get converted into a platform, okay, where it is broken up into zeros and ones. So this signal is given to a computer or a digital signal processor. Like my voice gets into the microphone, this microphone will actually convert, right? And then the system will take that or pick up that information and send it across via the channel, and from the channel it gets communicated to another client side or the receiver side. So sample and hold operation, okay, how does it work? As I told you, values are sampled, which means it is taken and then it is held for a certain amount of time. Then again it is taken and held for a certain amount of time, right? So this is how it will try to replicate the values of a sine wave. Okay, so you can see, okay, this staircase, okay, can be either smooth, okay, or it can be with the help of sample and hold. Why do I call it smooth? Because there is no much of holding time. Okay, immediately the next wave starts, but then here you can see there is a lot of holding time, right? So you cannot find that these staircase is smooth, but then here you can find more information, which means more staircases, right? So once the computer has its digital, then the binary signal is transferred, then there is a digital to analog conversion, then there's a staircase signal, and there is a smoothing filter, okay, which actually cuts off the noise and tries to make the information as usable as possible, and then this analog signal gets back to the plant. So in between this analog and digital, right, there are so much of processes that is happening, right? Okay, now We'll just look into few important points, right? So which I've listed out. External world or physical signals such as temperature, pressure, okay, or it could be vibration for that matter, okay, are converted to electrical signal for processing, and these are analog signals, right? So voice is converted to an electrical signal and then it's processed. So it's difficult to process and store analog signals. Therefore, we convert them to digital form and process it back to analog. So when we talk about the processing section, right, analog signals are not that good at processing, right? But then it's very good at accuracy, right? The accuracy, you still cannot beat an analog computer these days, right? So, uh, back then, many years ago, there used to be only analog computers. But then these days it's all digital computers, and then there are quite a few operations where for analog purpose, right? We will have to use those systems. Okay, now the other thing that we can look into is from the external world, physical signal is converted to electrical. So it's a reverse process, right? Voice getting converted to electrical, and from electrical it's getting converted to digital. From then again, it's the reverse process. So the physical signal is converted to electrical by the sensor, and that signal is converted to band limit, right? So that is what you see here in this anti-aliasing filter, right? So there's a conversion happening, okay, and we have this band limited signal, and that becomes the input of sample and hold circuit. Okay. Band limit signal by using the anti-aliasing filter to satisfy the Nyquist criteria. Okay. So the band limited signal is sampled at twice the rate more than the maximum frequency. So this is nothing but the sampling theorem, right? So Fs is equal to greater than or equal to 2 times of Fm, right? Fm is the maximum frequency, Fs is the sampling frequency, right? Okay. So the band limited signal is sampled at the rate of twice more than the maximum frequency of band limited signal, and this is held constant, okay, for a certain amount of time. Okay, so it's held constant till it gets converted. Okay, till what time? Till it gets converted to digital by ADC. ADC is analog to digital converter. Okay. Then the sampled voltage is converted to digital form to process and store the data. So processing, as I was mentioning, is comfortable, or we have developed systems for processing information based on only the digital format, because that's simpler, right, and compared to the analog form. Okay, so the sampled voltage is converted and it is stored and processed. This then is based on digital input that converts the digital data into analog signal. Fine. The output of DAC is a staircase, so its output is passed to smoothing filter to smooth the waveform. Right? So you can see here, okay, sample and hold operation, how I have the waveform, right? Then once it comes in, okay, it's a staircase signal, then I pass it to a smoothing filter, right? And you can see that the ups and downs are very less. It's almost in line with this sine wave. Okay, so it is smoothing the curve. Okay. Fine. So the next now we'll be looking into is DAC, digital to analog conversion. So we have a DAC here, a reference voltage, okay, the MSB bit, LSB bit. So it starts from D0, D1, D2, D3, D4, D5, okay, Dn, right, n minus 2, n minus 1. So the bits goes on towards the left hand side, and towards the right hand side I have my output voltage. Now since it's a digital to analog conversion, I need to give information in the form of bits, right? So bits are going to be in the form of zeros and ones. So which means if I'm using a 3-bit, like how I've used here, 3-bit DAC, so it's D0, D1, D2. So only these three we will be using. So this is starting from 000 and ending with 111, right? So if it's a 0 here, Okay, and now let's take for reference that it's 5 volts. The voltage reference is 5 volts. I give 5 volts here. Okay, and then I'm giving my input signals here in the form of digital binary values, right? So 000 I give, and the output that I'm going to get is about 0. Then if I give 1, okay, if D naught goes high, 001, then I'm going to get 0.625. Okay, then I still increase it. Okay, then 0.625 is again added and it becomes 1.25. Then again 0.625 is added, right, to 1.25, then it becomes 1.875. So the basic value here is 0.625, right? So based on that, it starts getting added up. So students, up till this point, are you able to understand? Yes. Up till this point, was it clear what all we are doing in DAC? How is the 6.25, right? How we got 1.25, is it clear?
Yes, sir.
Okay, good. So now we will next continue, okay, and we will see how these values are mapped. Okay, so you can see here that it is just getting added with 0.625 as we keep on increasing, and it goes to a point where it reaches about 4.375, right? 4.375. So that's the max. The reference that I'm giving is about 5 volts, and the inputs here, even if I give 111, is going to give me about 4.3, which is less than V reference. Okay, how is this V reference or sorry, V out calculated, right? So taking V reference into consideration, okay, V out is equal to K into V reference D divided by 2 raised to N. So that's the formula as to how this V out is computed, where D is nothing but the digital word, which means 000 or 111, whatever you're giving. Okay, for example, now let us take 3-bit DAC, and if the input word is about 110, okay, let us take that it is 110, then D is nothing but 6, okay, the digital word. So 4 plus 2, 6, right? Then D is equal to 6. For a 3-bit DAC, okay, N is equal to 3. So V reference is applied voltage to the DAC. So if we calculate that, right, so V reference is 5 and D is 6, 2 and N is 3 bits, right? So I should be getting about 3.75. So are we getting 3.75 here? Yes, with 110, right? So this is the formula. So you guys have to remember this formula, right? And this will be used in order to understand how V out occurs, right? So note down this formula. This is important. Okay, fine. So we can take anything for that matter, right? You can take probably 001 also and try and substitute. So if it is 001, then D is going to be 1 and V reference is going to be 5 and 2 raised to 3, right? So that should give me about 0.625. Okay, so this formula is important. Right. Okay, so moving on, the R2R ladder. Okay. The reason why we call R2R is because it has R and 2R values of registers, right? So both the values are there. And here, we will be giving the inputs, okay, via these registers. So B0, B1, B2. So this is my LSB, okay, and this is my MSB. So B0, B1, B2. And again, this is an op-amp here, okay, and this is the feedback register, of course the negative feedback, right? So how is this conversion happening? So inside now we know how this conversion is happening, what formula is used, and how are the bits mapping to the outputs, and when we utilize them in the formula, okay, how we are obtaining the values. So this part is clear. Now, how is this conversion done with the help of R2R ladder? So with the help of registers, how am I able to do? So I have to take the help of Thevenin's theorem. So I think you all know VTH, right? The Thevenin equivalent voltage, right? So we will be looking into that, and This V reference is nothing but the 5 volts that we give, right? This same thing that you see here, V reference, right? So that's the same thing here. And V naught is nothing but the output voltage, which is V out. Okay. So once we have these, information, right, using Thevenins, we try to continue. Okay. So the switch is either connected to ground or V reference based on the digital input. So this can be either connected to ground value, which is the lowest value, or it can be connected to the V reference value. So what is V reference? Here we have seen that it is about 5 volts, right? Fine. Now let us get into the circuit analysis and we'll try and understand how it works, right? So we're taking the same circuit here, right? B0, B1, B2, and I'm going to give 1 to B0, right? So wherever 1 is there, keep in mind, students, wherever 1 is there, now B0 is here, B1, B2. So wherever 1 is there, I'm giving V reference to that point, okay? So V reference is given. So VTH is nothing but 2 into V reference divided by 2R plus 2R. So we are using the formula here, okay, the parallel combination of 2R, right? So the Thevenin, okay, RTH. So I will take this as Thevenin equivalent resistance. RTH is 2R in parallel with 2R, which is nothing but R. So 2R, you will be putting the parallel formula for this resistor, right? So we try to get this converted to a simpler form, right? And we will be getting 2R V reference and the ground value, right? Now let us take the next section, okay, the next section here where I have R, 2R, okay, R and 2R. So R is here, 2R is also here, the same 2R, R, okay. So this is, I have now replaced this 2R and 2R with a Thevenin equivalent R, right? So that is my Thevenin equivalent here. And when I come to the next level, okay, this V reference is divided by 2. Okay. And if I go to the next level, then it's going to be V reference divided by 4. And if I go to the next level, it's going to be V reference divided by 8. Okay, so that's how it keeps on reducing, and the reference voltage is going to be divided, okay, as much as possible. Now, can someone do a quick math and tell me, right, how much is 5 divided by 8? 5 volts divided by 8, how much are we getting? Five you can divide by 8 and tell me how much do we get?
So 0.667.
5 divided by 8 is exactly 0.625, right?
Yes, sir.
So this 0.625 is nothing but the value which we were looking previously, isn't it? The first basic value, right? So this is how my R2R ladder will actually work. So again, now in the second circuit, what I'm going to do, the V reference is divided by 2, right? And I have replaced it with the Thevenin resistor, right? The RTH, and this R is remaining, right? 2R, R, and 2R. All these are remaining. Fine. Now I have to convert this, right? R and R becomes 2R. So again, I have 2R and 2R in parallel. So this will get converted to R, isn't it? So this whole thing is getting converted to R, and then R, 2R. But then what happens to my V reference? It's divided by 4. So whenever I keep on reducing, right, the V reference, also gets reduced. So now in the next step, right, you can see that I have 2R and then 2R. So that is nothing but going to be just R. So V reference divided by 8 and then R, right? So this is how, I am actually getting converted from one form to another form. So here you can see B0 is here, B1 is here, B2 is here. In the next step, it is only B1 and B2. So V reference divided by 2. In the next step, it's only B2 and it's V reference divided by 4. And in the next step, there's nothing and it's divided by 8. Right? So when I say nothing, it means it is 0, 0, 0. Is 0, 0, 0. Okay. So when it is 0, 0, 1, then it is 0.625, right? So this is what we saw here. Okay. So if you consider this, right, the Thevenin voltage, okay, 2R into, okay, 2R is nothing but here 2R into V reference by 4 divided by 2R plus 2R, right? So this will give me V reference divided by 8, and the Thevenin equivalent of the resistor is going to be only R. So 2R is here, 2R is here, and this equivalent will actually give me only R. So this is my final value, right? That is nothing but V reference divided by 8, which gives me about 0.625. Now, the Thevenin's equivalent circuit for binary value 0, 1, 0. Now, let us see how the 0, 1, 0 is going to work. Okay. So when it is 0, 1, 0, as I told you, wherever 1 is there, I'm keeping that V reference to that bit, right? B1 is high. B1 is high. So B1 is given Q V reference, right? So the same circuit is taken 2R, 2R, okay, R, 2R, R, 2R, right? So I'll be converting it. 2R, 2R will actually give me 2R in parallel combination with 2R plus R. So this whole thing I'm taking, right? 2R, 2R, and R. This whole thing is taken, and it is actually nothing but 2R. So this 2R comes here. This 2R is same as it is. R is here, and then 2R. Right? So this becomes my second stage of my circuit. So next thing is, I'll have to convert this 2R and 2R. So it should give me only R, right? So again, R plus R should give me 2R, right? So that is what I have written here, 2R and then 2R. Okay. Now, yeah, R, R, okay, 2R. So this is the next level, right? So this is V reference by 2. Okay. Now again, if I have to change this R and R, okay, so that is 2R. So 2R and 2R gives me only R. So that is V reference by 4. So you can understand that, when it's V reference by 4, which means 5 divided by 4, right? So how much are we going to get? 5 divided by 4. We're going to get about 1.25. Now let us go back and check if for 0, 1, 0, it is 1.25. Yeah. Yes. 0, 1, 0 is 1.25. Okay. So how does the circuit know that it has to stop there? Once we get the Thevenin equivalent, it's done. Right. So there's nothing more that you can reduce beyond this, isn't it? Beyond this, there is no reduction. And here we were able to, because the V reference was given here, so I had to first only check out this, and then I had to come here, and then I had to. So it was basically a 3-stage, right? Divided by 2, divided by 4, and divided by 8. So it was a 3-stage because the bit was here, right? So first, B0 is considered, and then B1 is considered, and then B2 is considered. Okay, but then here I can do it, just at 2 steps. Okay, and I'm going to get about 1.25, which is the same as I showed you in the tabulation column. Now, the Thevenin's equivalent for the binary value 1, 0, 0. So how is this going to happen? So which means this should be just one step, right? So 1, 0, 0. So B2 is going to get 1 B reference, and these two are actually 0, right? So which means when it is 0, right, how does it function? Okay, so let us see. So this gets converted, okay, 2R plus R, okay. So that gets converted to 2R, R, 2R, right? So how is it 2R? 2R parallel with 2R plus R is nothing but 2R. So that is this 2R that you're getting here, which is underlined here. 2R and plus R. Okay. Now after this, okay, we will see how this comes. So 2R is here, 2R and R. So this whole thing here again becomes 2R, right? So 2R and 2R. So this, once you get the equivalent, okay, that's when you start actually dividing. So 2R and 2R, right? So 2R voltage reference, and then ground. So again, if I have to reduce this, okay, if I have to bring it down, then it becomes R. So this is divided by 2. So 1 0 0. Okay, so 5 divided by 2 should be giving about 2.5. So let's check now if 1 0 0 is 2.5. 1 0 0, yes, it's 2.5, right? So this is how we actually reduce. First, whatever circuit you have, you try to reduce and get it in a simpler form. Once it's in just a single register at the top and at the bottom in parallel combination, that's when we start reducing. See here, we were not able to, because it was already reduced, right? So that's how you have to continue. Fine. Moving on, we will kind of generalize things now. Okay, so when it is 1 0 0, okay, I'm going to get B reference divided by 2. When it is 0 1 0, then it is B reference by 4. Okay, when it is 0 0 1, then it's going to be B reference divided by 8. Now let us say it is 0 0 0 1, then what is going to be my value here? B reference divided by, what is it going to be, students? After this, it's going to be, after V reference divided by 8, the next value is going to be how much? The next value is going to be divided by how much? 16, right? Okay, good. So whenever more than one bit is 1, then output of the ladder network is sum of the output voltages. Now let us say that I have 1 1 1. So in that case, I'll be adding divided by 8, divided by 4, and divided by 2. All three will be added, right? See, because for B2 it's divided by 2, for B1 it is divided by 4, and for B0 it is divided by 8. So all this will be added. Okay, and I'm going to take a common value here, right? And it's going to be 7 P reference divided by 8. So therefore the output of ladder network, okay, how is it going to be? It's nothing but B0 divided by 8, B1 divided by 4, and B2 divided by 2. Okay, so R2R network equivalent resistance is only R, because at the end we were having only R, isn't it? We were able to get it to the final value. So if I have to put them in the form of equation, right? So it is B0 divided by 2 raised to n. Why is it 2 raised to n? Because it is 8. So n here in this case is 3. So 2 into 2 is 4, and 4 into 2 is 8. So I can generalize it with an equation saying that it is 2 raised to n, right? Then B1 divided by 2 raised to n minus 1. So 3 minus 2. So 2 2s are 4. So 4 is here. So I'm kind of generalizing things here and bringing them in the form of an equation. Okay. Now, how is this final V out equation taken into consideration? So I have VR, okay, and this value gets into our op-amp, okay, and output is nothing but minus RF by R. Okay, minus. Why is it minus? Can someone tell me? Why is it minus? Because we've been learning this since day one. Why is it minus? In what combination is it? What kind of input have we given? We have given an inverting type, right? So because of this inverting, it is going to be minus RF by R. So this output is going to be minus RF by R. So this is going to be the gain factor into the input. Input is the voltage which is across the R2R ladder. So don't get confused that I'm seeing here something R-2R. This is just referring to the resistors R and 2R. Okay, so the value, so input, or you can call it as V in. So V in into gain. So gain here is minus RF by R. So what is my output? My output is nothing but V reference into the gain and the whole set of values that we looked into, right? So this is nothing but VR2R. Okay, so VR2R. So instead of VR2R, I'm using this equation, okay, and minus RF by R is coming here. Fine. So still, if I have to put this in the form of summation, right? So V naught is equal to minus V reference into RF by R summation BI. Okay, I going from 0 to n minus 1. So I have still generalized this equation in the form of summation. So 2 raised to n minus I. So if n is equal to 0, if I is equal to 0, okay, and whatever the bit values, so 3 minus 0, it will become 3, right? And this will become I, since I is 0, it is B naught. So B naught by 8. Is it the same thing here? Yes, B naught by 8. So we have generalized the equation in the form of summation. So this was our final equation, right, that we saw, with respect to the summation. Now the reverse process, right? So whatever we saw right now should be converted, back to its digital form, which means these analog values that we saw starting from 0.625 to 4.35, right? So that should be getting converted to its digital form, which is the reverse process. So all those you saw here towards your left hand side are right now shifted to the right hand side, right? And this is our input voltage, which is the analog input voltage. Say I give 0.625, right? So if the range is between 0 and 0.625, then it's going to assign the value 0, 0, 0. So at D0, D1 and D2, I should be getting 0, 0, 0. Now if the value, okay, if the input value is lying between 0.65 to 1.25, then it goes to the next level. So here also you can see that 0.625 is added to each and every value. So 1.25 plus 0.625. So here 1.875 plus 0.625. So all these are taken. So if it is, okay, if the V in value is less than, okay, or if this 4.375 is less than or equal to V in, then we'll be getting the value 111, right? So the reference again here is taken as 5 volts, right? And this comparison will happen between the input and the reference voltage. Now the next one that we will be looking into is counter type ADC. What is this counter type ADC? So we have seen a DAC, right, digital to analog converter, and we have seen a comparator. Comparator works like, checking the values between both of the inputs, right? And this will give, this is connected to a clock, which is AND gate. Okay, AND gate, one of the end is connected to clock and the other one is connected to comparator. So if the comparator value goes 0, which means here also I will have 0, and the AND gate also will totally be 0. And this binary counter is not going to get any inputs, okay? And so which means, directly it is going to have the output value, the digital output value. Now let us see step by step how it works, right? So in an analog to digital converter, the counter is reset to 0 by the count pulse. Okay, so this counter, whatever you are seeing here, right? So this counter, whatever you're seeing here, is actually converted to 0 by the count pulse. So if this becomes 0, okay, if this becomes 0, which means AND gate output is 0, so the binary counter is actually getting a 0. So this counter will actually be reset. Okay, so reset by 0 by a count pulse, and input voltage VA. Okay, input voltage VA. So input voltage is nothing but the analog input, okay, is applied to the comparator. So we are looking at ADC, analog to digital conversion. So analog input and digital output finally. Upon the release of reset clock is applied to binary counter. So after the reset, clock is applied to the counter and the pulses are counted by the binary counter. The number of pulse counted increases with time. So as time increases, the binary count also will increase. Now look at this waveform here, right? So 0, 1, 2, 3. So the counter keeps on increasing, right? That's an incremental counter. And the voltages here are slightly stepping up, right? And it will reach to a level where it is VA. So VA is nothing but analog input, right? So this is the clock pulse, okay, and this is the reset. Okay, so once I give the reset, then it stops functioning and the binary counter is set to 0. Okay, so yeah, the next thing, this voltage is compared with comparator when output of VD, okay, or output, that is VD, is less than the input voltage VA. So there is a comparison that happens here between VA and VD. Okay, so VD is nothing but from the DAC, okay, from the digital to analog converter, right? So this will give me the analog value and it will try and compare both the values. So if in case, let us say that VD is greater than VA, then what is going to happen? So this voltage is compared when VD is less than the input voltage. Okay, so when the output of the DAC, which is VD, becomes equal to VA, the output of the comparator becomes 0. So whenever there are differences, it is 1. Whenever it is equal, the value becomes 0. So once it becomes 0 here, the binary counter also will become 0. And the comparator becomes 0 and the AND gate disables the clock to the counter. So if there is no clock, then what will happen? This counter will stop. Okay, so the counter frequency should be less to allow the DAC for its conversion. So it should not be too fast, right? The counter, but then it should be slow. See, because these systems, we should be in sync. The systems are not in sync, then there can be chances of losing data. So we do not want that. Instead, we want a proper conversion to happen, right? So in order to have the proper conversion, we need to make sure that we are giving sufficient time. So how is that sufficient time given? With the help of frequency. So frequency should be made as low as possible, okay, to allow the DAC to function properly. So before it converts, if it sends the other value, then what is going to happen? We are not going to get the previous value, it is lost, right? So we have to wait for the previous value and then it gets in here into the comparator. It checks for the differences. If there are differences, it's going to be 1. If the differences are same, it's going to be 0, and 0 comes here. It's an AND gate. Irrespective of whatever clock you're giving, the binary counter stops, right? Okay, burst case delay is 2 raised to n minus 1 into t. So t is nothing but the time period, okay, which is 1 by f. Okay, so let's say, for example, if we are taking a frequency of 1 megahertz, okay, and n is equal to 12, then the delay is going to be 2 raised to 12 minus 1 microsecond, so which is about 4.095 milliseconds. So that is going to be the delay. So you have to wait for that delay between each clock pulses. Now, the other one is the successive approximation, ADC, SAR, okay, successive approximation register. So here also we have got a comparator, right? We have SAR here and we have D1, D2, okay, up till D7 or D8, okay. And then we have a clock pulses given and then DAC given. So DAC is also here, okay. The analog voltage is here, and then we are going to get the values, okay, in the form of digital, because analog inputs are given, okay, and we are expecting a digital output. So D0 to D7, so 8 bits is what we are going to get. So it takes the clock cycles to complete the conversion. So it has successive approximation register and DAC. So it has two main components: SAR, DAC, comparator. Three important things, right? So initially the SAR sets the MSB bit, which is D7 is equal to 1. So initially this will be 1 with all the other bits set to 0. So you can take this as D0, D1, D2, D3, D4, D5, D6, D7, right? So D7 is made high initially. So with output VD, okay, of DAC, so this is VD of DAC is compared with the analog input VA. So again here, the same concept, right? So if VA is greater than VD, then MSB is left at 1 and it remains the same value. Okay, so if VA is greater than this, so the output remains the same thing. Okay, the value remains same thing, that is 1 and all these zeros. Let's say for example that the analog input that you are giving here is less. Then what happens? It will convert it to 0. This 1 will become 0. If VA is less than VD, then MSB is made 0 and the output of SAR becomes totally 0. So it will only compare and check if VA is greater, same thing is retained. If it is low, then made 0. So this is repeated for all subsequent bits one at a time until all the bits in position have been tested. So this bit again, now this will go high, it will check, then this will go high, it will check here, 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 here. So that's why it's called successive approximation. One after the other, it is going to check and it is going to approximate the value. Okay, so when the conversion completes, okay, EOC, end of conversion signal, produces. Okay, so this is once we have finished all the bits, testing all the bits, EOC gets enabled, then I will know, okay, fine, I have finished this set, I can go with the next set. Right, now let us take this example. Okay, now V in is equal to 3.5 and we use 3-bit ADC with V reference 5. So at T1, okay, at T1, that is test case 1, okay, V in is 3.5 and my subsequent D2, D1, D0 will be 1, 0, 0, okay, and the DAC V out, let us take the DAC V out to be 2.5, okay, so it is compared here. So in this comparison, okay, we are seeing that the value of V in is greater than the DAC output, right? So the output is going to be 0, which means it is going to retain the same thing, right? Now let us take this case where V in is less than the DAC output. So this is like VA and this is like VD. Okay, so if this is less, then what is going to happen? The comparator output is going to go high, okay, and this bit is actually taken here, 1, 0, 0 is taken here, okay, and since it goes high, okay, so this bit is made 0. Okay, this bit is made 0, so which means 1, 0, 0, it should be giving me about 2.5. Okay, so that is the output. Now let us take in the next case where it is 3 and 3.125. Okay, so here it is 3.5, which means it is greater. Okay, so comparator output is going to be 0. No changes are done to these values. 101, right? 101. So which means the same thing is retained. Okay, which is 3.125. The same value is retained. It is not changed because this is greater. Okay, so that will actually change only when only when V in actually becomes greater. Okay, so this is how the approximation works with the SAR. Okay, so with this, we actually complete the sections, the module 5 and the whole of your syllabus with respect to linear integrated circuits. So students, do you have any doubts with respect to the concepts discussed today? Were you all clear with these concepts? Any doubts? Any concerns?
No,
Yeah. Is it all fine? Bhumika,
yes, sir.
any doubt?
No, sir.
Okay, so I'll be sharing this as well to you all. Okay, so you can actually refer it for your studies. And if needed, okay, then we can probably look into another dimension of this SAR and ADC. So just let me know. Okay, probably we can plan out another session if in case it is needed.